Hi everyone, the channel Easy Lecture welcomes you. In this video we are going to discuss about Fourier transform. So to understand this I have taken some problems asked in Anna University semester examination. So in this video we are going to solve two problems completely which were asked in semester examination, and after that we are going to also analyze the other problems of same kind asked in semester examination. So this video is going to be very much useful, so watch till the end. Before entering into the video, subscribe my channel Easy Lecture. Now let us go for further discussion. Okay, the first question that we are going to discuss here is find the Fourier transform of x of t equal to e power minus a modulus of t provided a greater than 0 and sketch its corresponding magnitude spectrum. Okay, so this is the question asked and a signal is given. We are asked to find the Fourier transform of the signal. Now the question arises, why do we need to find the Fourier transform? Why should we apply Fourier transform to a signal? Okay, so what does this Fourier transform do? Okay, actually this Fourier transform, it converts a time domain signal into frequency domain signal, and here in the question also you can see the signal in time domain. So there is a time notation t mentioned in the appearing in the signal. Okay, so this should be converted into frequency domain. So why do we convert a time domain signal into frequency domain? So the answer is very simple. If a signal is represented in time domain, the analysis become complex and we cannot get more information from the signal. Okay, whereas if it is converted into frequency domain, the signal can be analyzed, processed very easily. Okay, so, and that is the reason why we convert a time domain signal into frequency domain signal using Fourier transform. Okay, so here for example, a signal, it is required to get transmitted from one place to another place, from transmitter to receiver. Okay, and during transmission it should not get affected by noise, it should not get influenced by other noises. Okay, and even if they are getting influenced, even if they are affected by noise, they should be removed in the receiver, and they should not be hacked. Without hacking, they should reach the destination place, and these are the reasons why we analyze the signal. So what kind of carrier we can add, how can we strengthen the signal? So these kind of processings are required, and even we may transmit a photographic signal instead of a text signal, and we need to process these signals. We may transmit a video signal. So these things have to be processed, and for processing purpose, if the signal is transmitted into frequency domain, the processing becomes easier, and a lot of techniques can be applied in the frequency domain signal. Okay, but it is not understandable by the humans, by the users. So again, in the receiver side, the time domain signal, the frequency domain signal should get converted into time domain signal by inverse Fourier transform, and this is the reason why we go for Fourier transform and inverse Fourier transform. Now let us focus in this problem. So there is a signal given, we need to apply the Fourier transform for that, and the formula that we use here is x of omega equal to integration of minus infinity to infinity x of t into e power minus j omega t dt. So here omega comes, that is the representation, the notation of angular frequency. Here t comes, that is the notation of time domain. So here the time domain signal is converted into frequency domain signal. So that is what we are going to do ultimately. Okay, so here in the next step, instead of x of t, we are going to substitute the value of x of t equal to e power minus a modulus of t, and x of omega equal to integration of minus infinity to infinity e power minus a modulus of t into e power minus j omega t dt. In the next step, we are going to split the integration into two parts. One is from minus infinity to 0, another one is from 0 to infinity. Minus infinity to 0, this integration is from 0 to infinity. Then from minus infinity to infinity, modulus of t takes the value, becomes minus t, and from 0 to infinity, modulus of t becomes plus t. Okay, now we are going to factorize this, we are going to simplify this. So minus a into minus t is plus at. Okay, so we will be getting e power at into e power minus j omega t dt, that becomes e power at minus j omega t, and t can be taken common outside. So like that process can be done. And similarly for this part of the signal also, we can have taking minus common outside, it becomes minus and t are common, so it becomes e power minus of a plus j omega the whole into t dt. So it becomes like that. Okay, so that is what we have done here. Okay, and finally the signal appears as e power a minus j omega into t dt plus integration of 0 to infinity e power minus common taken outside a plus j omega into the whole into t dt. Okay, and when we apply integration to an exponential signal, here for this signal we will be getting e power a minus j omega t divided by a minus j omega. Then for this signal we will be getting e power minus a plus j omega t divided by minus of a plus j omega. Okay, so this is for exponential signal, and after that we have to apply the limit also. Okay, so e power a minus j omega t divided by a minus j omega, and the limit is from minus infinity to 0. Similarly, in the second part it is e power minus a into plus j omega, e power minus a plus j omega the whole into t divided by minus of a plus j omega, and the limit is from 0 to infinity. Now we have to apply the upper limit, and also we have to find the value applying the upper limit, find the value applying the lower limit, then we have to perform upper limit minus lower limit. Okay, so that is what we are going to do now. Okay, so here when we apply the upper limit we will be getting 1 divided by a minus j omega. So here let me solve this. When we apply the upper limit 0 for this part of the equation, it becomes e power instead of t we have to apply 0. Okay, because we have integrated with respect to t, so we have to replace the value of t by the limits provided. E power a minus j omega into t becomes e power a minus j omega into 0, and that becomes e power 0. E power 0 is equal to 1 divided by a minus j omega. Okay, then minus lower limit, lower limit is e power a minus j omega into t, and for instead of t we have to substitute minus infinity, so that becomes e power minus infinity. E power minus infinity can be written as 1 divided by e power infinity. We know the value of e power infinity as infinity, so 1 divided by infinity becomes 0. Okay, so that is why this portion is eliminated, and we have only 1 divided by a minus j omega as we got here, as we have solved. Okay, now let us talk about the second part. Again we are applying the upper limit and then lower limit, and subtracting the lower limit value from upper limit. Okay, so when we apply the upper limit here, it becomes e power minus a plus j omega into infinity. So that becomes, since we have a negative sign here, it becomes e power minus infinity. E power minus infinity is 0. So 0 divided by minus of a plus j omega becomes 0. Then minus of, again we have to apply the lower limit. So we have applied the upper limit minus applying the value after applying the lower limit. When we apply the lower limit, it becomes e power minus at into j omega into t, and t is replaced by 0. So 0 e power 0 becomes 1 divided by minus of a plus j omega. So this minus and minus they are getting cancelled, and we are having plus 1 divided by a plus j omega. Okay, so this is the Fourier transform applied to e power minus a modulus of t provided a greater than 0. Okay, and now we have to solve this. Okay, so here we are finding the LCM and we are writing this equation. It becomes 2a divided by a square plus omega square. Okay, so this is the Fourier transform of the signal, and now we are asked to find the magnitude response and phase response. So magnitude response, what is the magnitude of this signal after after applying various values for omega? So that becomes magnitude response. After for different values of frequency, what is the magnitude, and for different values of frequency, what is the phase? That becomes phase response when we plot the signal. Okay, so that is what we are going to find now, and there is a simple way to find the magnitude response and phase response, and we have discussed about this already in control system videos. So I am writing here, if a signal is a complex signal a plus jb, so here I am writing it as a plus jb. To find the magnitude of the signal, we can write square root of real part square plus imaginary part square, a square plus b square. So this is the magnitude of a plus jb, and to find the phase of a plus jb, it is equal to tan inverse of imaginary part divided by real part. So you do not get confused, it is tan inverse of b by a, imaginary part divided by real part. So that is what we are going to do here. Okay, so for this equation, so here we have x of omega equal to 2a divided by a square plus omega square. When we find the magnitude response or the value of magnitude, the magnitude equation for this it is square root of imaginary real part square plus imaginary part square. We do not have any imaginary part is 0. So finally we have square root of 2a divided by a square plus omega square the whole square. So the root and the square, they are cancelling each other. Finally we have the magnitude as the same equation 2a divided by a square plus omega square. Okay, so that is what we have got. The magnitude of x of omega equal to 2a divided by a square plus omega square. Now we are varying the frequency for different values of angular frequency. What is the magnitude that we are going to find? Okay, so here in the question it was given us the value of a is greater than 0, so we are assuming the value of a to be 1. Okay, so for different frequencies and for a equal to 1, what is the magnitude? So that is what is represented in this table for omega equal to 0. So here we have omega independent variable. For omega equal to 0, the magnitude is 2, because 2 into 0, sorry, 2 into a is 1, 2 into 1 divided by a square plus omega square, 1 square plus omega square is 0 square, so it becomes 2 divided by 1, so that is equal to 2. So that is what we have got here. And when we apply the value of 1 for omega in this equation, we will be getting this equation as 1. Similarly the same value for when we apply omega equal to minus 1, because here in this equation we have omega square instead of omega, so there won't be any change in sign. So whatever we get here, it is not 0.5, it should be 0.4, because when we apply omega equal to 2 in this equation, it becomes 2 into 1. The value of a is 1 divided by 1 square plus omega equal to 2, so 2 square. So that becomes 2 into 1 is 2 divided by 1 plus 4, that is equal to 5, and that value is 0.4. Okay, so this is what we must get here. Here there is a mistake, it is not 0.5, it is 0.4, similar to the thing that we have got here. So there is a typing mistake, right? So we have got the values of different magnitude for different values of frequencies, and now we are going to plot it. Okay, this is how we will be getting. Okay, along x-axis we have frequency, and along y-axis we have the magnitude of the frequency domain signal. For omega equal to 0, the amplitude is 2, okay, the magnitude is 2. For omega equal to minus 1, and also for omega equal to 1, the magnitude is 1. Okay, for omega equal to 2 and minus 2, the magnitude is 0.4. So this the picture that you are seeing in the page, so that gives the magnitude response of the given given frequency domain signal. Okay, next we have to find the phase response. When we talk about phase response, it is tan inverse of imaginary part divided by real part. So in the frequency domain signal there is no imaginary part, so it becomes tan inverse of 0 divided by real part. The real part is 2a divided by a square plus omega square, so we will be having tan inverse of 0. Tan inverse of 0 is 0. Okay, so here we will be having the phase response like this. Along x-axis we have the angular frequency, and along y-axis we have the phase pi equal to tan inverse of x of omega, or angle of x of omega, and that is 0 for any value of omega. So there is no phase, the phase is 0 for any value of omega. So that is what we have got from this question. So this question is getting over here. Now we shall discuss what are the other problems of same kind asked in university examination. So here is the first question. It is x of t equal to e power minus 8 into u of minus t provided a greater than 0. This is similar, it is similar to the question that we have discussed so far. Okay, so this kind of question is asked in April-May 2019 examination, regulation 2013, and the subject code EC6303 signals and systems. Okay, so here we have u of minus t, and in the question that we have discussed, we have not got any step response, or it is not influenced by any step signal. We directly got e power minus a modulus of t. So when we have the time reversed step signal, the integration will take the limit from minus infinity to 0, because from minus infinity to 0 u of minus t is 1, whereas from 0 to infinity u of minus t is 0. So we will have the integration limit from minus infinity to 0 for this question. Okay, and when we talk about the second question, so it is also similar to the same question, and this question was asked in the year April-May 2019 under the in regulation 2017 under the subject code EC8352 signals and system. Okay, now let us talk about the next signal. X of t equal to 1 for modulus of t greater than less than t1, and 0 for modulus of t greater than t1. So we will be having the signal like this. So this is x of t. Along y-axis, along x-axis we have the independent variable t, and this question will be, this representation will be like this. This is minus t1, this is plus t1. So it is a rectangular signal, and for this signal we have to find the Fourier transform. The amplitude between minus t1 and t1 is 1, and for in all the other positions the amplitude is 0. Okay, so we have to apply the rectangular we have to apply Fourier transform to this rectangular signal, and we can derive the frequency domain representation of the rectangular signal. Okay, in the same formula we can apply. Now let us discuss another one problem, which is a unit del function. It is a delta function, unit impulse signal. Okay, so find the Fourier transform and sketch the responses for x of t equal to del of t minus 5, and this question is asked in April-May 2019 examination, regulation 2017 under the subject code EC8352 signals and system. We have represented this signal in the diagrammatic form here. Along x-axis we have time, because it is a time domain signal, and along y-axis we have this signal. It is a unit impulse signal. We have talked a lot about unit impulse signal. So unit impulse signal has the amplitude of infinity, but the area under the curve is 1, and that is why it is called as unit impulse signal. As an example, we have seen a lot of examples that represent a unit impulse signal. For example, the clapping of hand, the instant at which both the hands they collide, so that is at that point the signal appears. So that is impulse signal. Whereas step signal, it appears for the entire period where t is greater than 0. But impulse signal is not like that. It appears only at that particular instant. We can also quote another example, a cricket ball hitting a bat. So that is also an example of unit impulse signal. Okay, so we can have a lot of examples. Okay, and collision, always collision, they are unit impulse signal. Okay, only at that point we will be having signal, and that is why this unit impulse signal is used to convert a digital signal, a continuous signal into discrete signal. And when we multiply this impulse signal, time shifted and many time shifted impulse signal, when we multiply that signal, we call it as a comb signal. With any continuous signal, that will be converted into discrete signal, and we have seen this already while discussing digital communication. Now back to this problem. Okay, so we need to find the Fourier transform of this. Again, we are applying the same formula, x of omega equal to integration of minus infinity to infinity x of t into e power minus j omega t dt. We have to replace x of t by the impulse signal del of t minus 5, and del of t minus 5, it is appearing only at the instant t equal to 5. For all the other values it is 0. So when 0 is multiplied by e power minus j omega t, it becomes 0. Only at t equal to 5 we will be having the signal, and the area under the curve of impulse signal is 1. So we can have integrate e power minus j omega t at t equal to 5. For all the other values of t, the signal becomes 0. So this is for other values. For other values except at t equal to, for other than t equal to 5 will be getting 0, and only at t equal to 5 will be having the signal. So for impulse signal alone, we do not have to go for integration. We can directly write this e power minus j omega t at t equal to 5, and we are replacing the value of t as 5. Okay, so we will be getting the frequency domain signal as e power minus j5 omega. We have found the Fourier transform of x of t equal to del of t minus 5. Now we have to go for magnitude response and phase response. When we speak about magnitude response, we know already it is square root of real square plus imaginary part square. So here this exponential complex exponential signal can be rewritten in a trigonometric notation as cos of phi omega minus j sin phi omega. We know that e power j theta equal to cos theta plus j sin theta, e power minus j theta equal to cos theta minus j sin theta. So we have applied that Euler's formula to represent this e power minus j phi omega as cos of phi omega minus j sin phi omega. And now we are going to find the magnitude of this signal. So cos square of phi omega plus minus of sin phi omega the whole square. So that becomes cos square phi omega plus sin square phi omega. So cos square a plus sin square a is 1. We know that already. We have got x of omega equal to the magnitude of x of omega equal to root of cos square phi omega plus sin square phi omega. So that is equal to 1. Okay. Now we have to find the phase. So when we talk about phase, it is tan inverse of b by a, tan inverse of minus sin phi omega divided by cos phi omega. So that becomes like this. So angle of x of omega equal to tan inverse of minus sin phi omega divided by cos phi omega. It becomes tan inverse of minus tan phi omega. Tan inverse and tan are getting cancelled, and we will be having minus phi omega as the phase. When we plot this magnitude and phase in graph, we will be having, okay, so for magnitude response, whatever the value that omega may take, the magnitude is always 1. There is no change in it. Okay, so this was taken from this. So for impulse signal, we will be having the magnitude as 1. For whatever the frequency, the magnitude of impulse signal in frequency domain is always 1. Okay, right. Now when we speak about phase, when we plot phase response of the impulse signal, at omega equal to 0, the angle is 0. At omega equal to minus 1, so here along x-axis we have omega. At omega equal to minus 1, we have the angle as minus 5 into minus 1, that is 5. For omega equal to minus 2, we have the angle as minus 5 into minus 2, that is 10. Similarly, at omega equal to 1, the angle is minus 5 into 1, that is minus 5. For omega equal to 2, the angle is minus 5 into 2, that is minus 10. So we will be having the, we will be getting the phase like this. Okay, so I have not connected the dots exactly, but the dot should be connected, and it is a kind of a ramp signal. It represents the shape of a ramp signal. Okay, so this is how we can find the Fourier transform of the signals, and this is how we can plot the magnitude and phase spectrum for the frequency domain transmission that we apply to the time domain signal, okay, using Fourier transform. Okay, I hope you might have understood the reason why we go for Fourier transform and what Fourier transform does, then how to plot the magnitude response and phase response. I hope all these things are clear. Meet you again in another video that uses the properties of Fourier transform to find the frequency domain signal of the given time domain signal. Okay, so we shall meet again in another video. Until then, bye. Thank you.